So in this section, we're taking all those properties that we learned in the previous section about parallel lines and the angles formed by them, and we're going to apply them to algebraic problems. Now, it seems weird that the warm-up, what we're doing is solving equations, but we're going to need those later. So let's go ahead and make sure we know how to do these. So number 1 and number 2 are both what are called quadratic equations. They have that x squared term. So there's a couple ways to solve these. One is to factor, and that's what I'm going to do with number 1. But to factor, I need to have everything over on one side. So I've got to bring my 6x over. I've also got to add 1 to both sides. So I'm going to have x squared minus 6x plus 8 equals 0. Everything on the right canceled out. At this point, I want to factor, so I want numbers that multiply to 8 add up to negative 6. I'm looking at a negative 4 and a negative 2. So x minus 4 equals 0. X minus 2 equals 0. So x is either 4 or 2. Number 2, an easier way to do this is to solve by reversing operations. So again, we have that x, we squared it, we subtracted 7, and we got 42. So let's work backwards with that. Let's add 7. And then take the square root. When we take the square root of both sides, we're going to end up with that plus or minus the square root. So x equals plus or minus 7. 3 and 4 are exponential equations, and in order to solve these, well, the easiest way to do it algebraically anyway, is to make sure that they have the same base. So on number 3, they already do. The base here is that 2. They're equal. So the bases are the same. If this equation is actually true, then the exponents have to be equal as well. So I know that 3x plus 2 has to equal 5x minus 6. And I can solve that by taking away 3x, adding 6, and dividing by 2 gives me x equals 4. On number 4, we do need to change the base of the 27. We want to get it down to a 3. 3 to the 2x is already good. 27 is 3 to the 3rd power. And then so in the next line, when we distribute the exponent, so distribute the 3 to both parts of that other piece of the exponent. Let me rewrite that x. It's looking a little gross there. All right, there we go. We get 3 to the 3x minus 3. The bases are the same. I set the exponents equal. And I solve. So I'm going to take 3x away. So x has to equal 3. So getting to the activity 1 here, again, we're taking all those things that we learned about parallel lines, and we're going to apply them and use whatever we need to solve these problems. Just a note about notation. When we see those symbols right there, that means that those lines are parallel. So I know that for sure. I want to look at the two angles that I have given here, 2x minus 10 and 65 plus 3x. They're not corresponding, alternate interior, alternate exterior, any of those special relationships we have. So we've got to kind of think about a backdoor way to get these measurements. Well, there's a couple things we can do. I do know that these angles right here are alternate interior. So if this angle is 2x minus 10, this one here has to be 2x minus 10 also. I also know that if two angles are right next to each other and they form a straight line, they're supplementary. So what I'm going to do then is take 2x minus 10 plus 65 plus 3x, and I'm going to set it equal to 180. Combining terms, I've got 5x plus 55 equals 180. And when I subtract 55 from both sides, I'm going to get 125. So x is 25. I want to find also the smiley face angle. So another way to do that is I can find out 2x minus 10 and find the supplement, but there's an easier way to do that. I can look at these two angles right here, and I know that those have to be equal because they're corresponding. So when I plug in 25 into this angle, I'm going to get 65 plus 3 times 25 is 75, which gives me 140. So then the smiley face angle must be 140 degrees. All right, so again, I just used the fact we had alternate interior. If you wanted to, you could use the vertical angles here to get this measurement and then use alternate exterior angles or supplementary. That's a possibility as well. Let's look at, let's pick out a good one here. Let's do number 5, 7x minus 8 and the 62. Again, parallel lines from that symbol right here. And if I'm looking at this angle and this angle, they are same side interior angles, so I know they have to be supplementary. So I'm going to add them up to 180. And I've got 7x plus 54 equals 180. 7x is 126. So when I solve for x, I'm going to get 18. I want to find the smiley face angle. The best thing for me to do then is plug into the vertical angle right here. Once I do that, that makes things a little bit easier. All right, so I know that 7x equals 126. I know that from this part right here. So when I solve for this angle, I'm going to get 118 degrees, and the smiley face is vertical to that, so that's also 118 degrees. And then number 3, it looks like we have what are called alternate exterior angles. So we know that these angles right here are going to be congruent. So once I find out what x is, I can easily find that smiley face angle. It should be fairly easy to find x. 2x plus 10 equals 86 plus x. So x is 76. Now, probably the best thing to do is take that and plug it into here, the 2x plus 10, and then just find the supplement. Because that smiley face is next to it, they form that straight line. We know they add up to 180. So when I plug 76 into 2x plus 10, I'm going to get 2 times 76, which is 152. Add 10, we get 162. So the smiley face angle, again, is 18 degrees. Again, not drawn to scale. That's key there. That you're like, it's not 18. Well, it is 18 degrees based on the measurements that we have. And then let's take a look at number 10. This one's kind of an interesting problem here. We want to find out what W, X, Y, and Z are. We have all these different angles. Now, here's the cool part with this. We actually end up having 2 pairs of parallel lines, here and here. Here and here. And later on, you're going to learn that we have a special name for this shape right here. It's called a parallelogram because both pairs of opposite sides will be parallel. So first thing I'm going to do is find out what x is, because that's probably the easiest one. So actually, you know what? Y is probably easiest. These angles right here are corresponding, so they must be congruent. Similarly, Z is also corresponding with angle Y. And W is alternate interior with angle Z. So then all I really need to do then is find out what x is, and there's a lot of easy ways to do this. But probably the best way is I'm going to look right here and find these 2 angles being supplementary. So 180 minus 117 will end up giving me 63 degrees. So again, I've got these 4 different measurements. 3 of the angles ended up being exactly the same, just based on where they're located. All right, so let's do the closure here and make sure we understand why things can be parallel, why they can't, based on measurements. So if lines A and B are parallel, so we can make that measurement right here, explain why the value of x cannot equal 20. So probably what I'm going to try to do is just plug 20 in for x. Take 5 times 20, you get 100. Take away 40, you get 60. And then plug 20 down here. 3 times 20 is 60, plus 20 is 80. Now these angles right here are they're corresponding angles. So if those lines are parallel, I know that these angles must be congruent, and I don't see that. When I plug those numbers in, then it just doesn't work out. So corresponding angles are not congruent. That's a huge problem if the lines are parallel. So now in question 2, we're kind of flipping, saying, all right, let's say we know they're parallel. What value of x do we have to have? So to do that, I'm going to take those two angles, I'm going to set them equal. 5x minus 40. 5x minus 40 equals 3x plus 20. So when I solve for x, I'm going to take away 3x, add 40, and I end up getting x is 30. So kind of close to what we had before, but not exactly the same thing. So we're looking for x to be equal to 30. So again, we're using the relationships we had in the previous section, just setting up algebraic equations and solving those from there.